Over 2,300 years ago, Euclid proved that the primes are infinite. Since that time, no one has been able to locate every single prime. Until now. Following is a visual algorithm designed to locate every single prime number.
A prime number is a natural number greater than 1 that has no positive divisors other than 1 and itself. A natural number that is greater than 1 that is not a prime number is called a composite number. For example, 5 is a prime number because 1 and 5 are its only divisors. 6 is a composite because its divisors are 2 and 3, also 1 and 6. So any number that is not a prime is called a composite, and it's composed of numbers other than 1 and itself. So you can see in the first row here that we've got 1, 2, 3, 5, 7. All of these numbers in the first row are prime numbers. They're in yellow, and their only divisors are 1 and themselves. Once you get to 4, this is a composite number, so is 6, 8, and 10, and so is 9. There's good news. If you don't have a brain for numbers, we've got one that you can borrow. The property of being prime is called primality, and there's a number of tests. Goldbach's conjecture is one of the oldest and best known unsolved problems in number theory and all of mathematics. It states, every even integer greater than 2 can be expressed as the sum of 2 primes. You've got the Miller-Rabin primality test. It's an algorithm which determines whether a given number is prime, similar to the Fermat primality test and the Solovay-Strassen primality test. It can be a bit complicated. There's the AKS primality test, known to produce only probabilistic results. They're talking about very complex mathematics. We are offering a much simpler test for primality, and this test that we're offering here is based on an algorithm. We call that algorithm a cynosure continuation algorithm, and we're going to demonstrate today exactly how that algorithm works. Here, we use a cynosure continuation set from 1 to 100 and from 101 to 200. And these two sets have prime numbers exposed in yellow and non-prime numbers in blue and red and in white. What columns we isolate here, 1, 3, 7, and 9. These are the cynosure numbers. These numbers continue on the second cynosure continuation set from 101 to 200. And you'll see that we have a column where 1, 3, 7, and 9 continue. Now this will go on infinitely. One of the details that many people would notice right off the bat is that 2 and 5 are unique. 2 is a prime number, so is 5. The interesting thing about 2 and 5 are that they are so close to the origin, which we call 1. And because they're in this row, close to the origin, there are few numbers before 2 and 5. So there aren't going to be any divisors other than 1 and 2 itself, other than 1 and 5 itself. Just by glancing at these cynosure continuation sets, a light bulb might go off in your head. If not, we've got one here for you. The key to using the cynosure continuation algorithm is to locate patterns. These are deterministic patterns. They're not probabilistic, so there's no complex formulas and calculations to make. By probabilistic, mathematicians are looking for something very sophisticated, patterns that are probable. Instead, we are going to produce an algorithm that is not probable, it is exact. The cynosure continuation algorithm works like a good detective. Now, a good detective trying to find the prime numbers would try to eliminate those things that are not primes, the non-prime numbers. eliminate those, and it'll be a lot easier to find the primes. Eliminate the suspects who could not possibly commit the crime of being a prime number. Eliminate those, and then you'll find the suspect. So the process of elimination gets rid of 2, 4, 6, 8, 10. In the cynosure continuation set from 1 to 100. But it also eliminates 102, 104, 105, 106, 108, 110. It eliminates those columns completely. So now we have to eliminate non-prime numbers within the cynosure continuation columns. We can see that 3, when it's squared, gets us over to here, a red box. These are perfect squares. They are not prime numbers. They are eliminated. So within the cynosure continuation columns, we are already starting to eliminate non-primes. Once we move from 3 to 7, when we square 7, that gets us over to here, a red box, perfect square, not a prime number. 9, square that, and you get to 81, perfect square, not a prime number. Now we get over to here, to 11. We square that. Where does that take us? That takes us to a perfect square, 121. It's in the cynosure column. If you didn't catch on to the fact that we're using the number 1 as a prime number, well, we will show you how to catch on to things. Grab one of these and practice. Practice makes perfect. The cynosure continuation algorithm is based on a cycling process that goes from row to row to row to row, and this continues throughout the entire number system infinitely. To help you visualize this cycling process, we've got something of a cycle. Actually, that was a chariot. 3 times 7 gets you here, non-prime number. 3 times 9 gets you here, which is a non-prime number. 3 times 11 gets you here, a non-prime number. You could use one of those fishy algorithms that are extremely complicated, but aren't you glad that we decided to use an algorithm with different colors? An algorithm that separates numbers into columns. Aren't you glad that we point out all of the prime numbers in yellow, all of the non-primes in blue and white, of course, and also in red? Now you'll notice a very fascinating modification going on here, where 7 times 7 gives you 49, but notice that 7 enters the algorithm at this point, so that you can see 7 times 9 over here, and 7 times 11 here, 7 times 13 here. We already saw that 3 times 3 is 9, 3 times 7 is here, 3 times 9 is here, and we see that pattern starting. Now we're beginning to see 7 starting that pattern over here, then 7 times 9 over here, then 7 times 11 over here, then 7 times 13 over here. 9 times 9, which is 81. 9 times 11 gets us here, 99, in cynosure continuation column, the 9 column. 9 times 13 gets us, oh, sometimes you need a helping hand. 9 times 17, right here. We covered 3, we covered 7, and we covered 9. Continuing with the number 11, which is a prime number, we square that, we get to 121, which is a perfect square. 11 times 13 is going to get us to a non-prime number, and that is exactly here. That helping hand comes in very handy. Continuing with the pattern, 11 times 17 should produce another non-prime number in the cynosure continuation column, and that's exactly here. We've got the number 13, which when squared produces a perfect square, 169. The pattern continues 13 times 17, which would produce a non-prime number somewhere in one of the cynosure continuation columns that are extending toward infinity. Where is that 13 times 17? I feel like I'm at the train station and the train's pulling in. We have 13 times 13 producing 169, which is in the red box, is a perfect square, and it's a non-prime number within one of the cynosure continuation columns. 13 times 17 brings us here. Notice it's in a blue box. That is a non-prime number. 13 times 19 brings us right here. Thank goodness for that helping hand. We're cycling through all of these layered cynosure continuation patterns, and we notice that the prime numbers appear to be randomly spaced out throughout the natural numbers, but they're not. There's nothing random about it. Although it might appear to be random, these things are precisely determined by the structure of the number system itself. There are other methods, probabilistic methods, to locate prime numbers. Those are sort of a derivative from the harmonic series. Such as the Riemann zeta function. These are infinite series that sort of predict prime numbers, but in a very probabilistic fashion. We argue that it's much easier to find these prime numbers. It's much more deterministic, and it's based on structure. Okay, we've already seen that the square roots of numbers within the cynosure continuation columns produces a new cycle of numbers that are not going to be prime. We went from 7 to 9 to 11 to 13 to 17. We're going to look at 17 right now, and then we're going to look at 19. Since the numbers seem to be progressing toward infinity, I think we should be a little brief. To be brief, this is going to cost you big bucks, because this is leather. It's going to cost you $199 plus shipping and handling. So we've got 17 times 17, 289. We've got 19 times 19, 361. And you're going to notice that the 3's continue. 3 times 71 is 213, a non-prime number. The 7's continue. 7 times 33 is 231, a non-prime number. The 9's continue. 9 times 27 is 243, a non-prime number. The 11 continues. 11 times 23 is 253. The 13's continue. 13 times 21 is 273. So now we know that 17 starts a new cycle, will be 17 times 19. 19, which is a perfect square here, 361, is going to start another cycle with 19. Then we go to 21, which is going to start another cycle. 19 times 19, a perfect square, which produces 361. Now we would expect to see 19 times 21 producing a non-prime number within one of the cynosure continuation columns. Where is it? That helping hand comes from all quadrants. Okay, here we have 21 times 21, a perfect square, 441, and we notice that the 3's are continuing, the 7's are continuing, the 9's are continuing, the 11's are continuing, 13's are continuing throughout here, and 21 times 23 should be here somewhere. 21 times 23 produces 483. which is a non-prime number within one of the cynosure continuation columns. In conclusion, it is very clear that the cynosure continuation algorithm will work. It will locate every single prime number by eliminating strategically those numbers that are not prime within the cynosure continuation columns. All of those numbers that are yellow are prime numbers, and you can see that it was well worth the wait, because mathematicians have been waiting for 2,000 years. Yes, that's 2,000 years. Yes, ladies and gentlemen, it has been 2,000 years since Eratosthenes started looking for prime numbers.
More is to be found in our book, out in print in a week, The Definitive Infinitary. As a fringe note, it proves the Riemann hypothesis, which has not been proved in 150 years. And it does so by using a similar pattern to this in looking for the structure to the numbers.